Why has science in general assumed that consciousness is not fundamental? Why haven't we observed a simple, thing that you're observing like you're doing yourself? Why have we dismissed this notion that consciousness may be fundamental within science?
Partly because we've never had a mathematical theory of it, right? If you don't
Mhm.
have a theory of it, what can you do? People, it's just a word. I could say, the Green Goblin is the fundamental reality. Well, who cares? I called it the Green Goblin, but what's your theory of the Green Goblin? What does it predict? So, since people studying consciousness have never before had a mathematical theory that predicts anything, there's literally nothing for science to take seriously. There's nothing on the table. So it's been a debate in which the consciousness side literally brings nothing to the table of interest. And so it's time for us to bring something. We've had experiments, but if you have experiments and no theory, you basically have nothing. You have to have a mathematical theory, and it has to be testable and precise, or you're not, or scientists won't give you the time of day. And I understand. I'm a scientist. I completely understand. That's why I'm going after a mathematical theory, because I know that that's the starting point for a true scientific investigation and dialogue. So, and I have a lot of friends who've been looking at paranormal phenomena and so forth, and in good experiments. But I've told them for many years, you will get no traction whatsoever because you have no explanation in terms of a theory, right? So like Daryl Bem had this very famous experiment in which he got precognition effects, 400 milliseconds. He claimed that his subjects could tell by their autonomic responses 400 milliseconds ahead of time what he was going to show next on the screen. But he had no theory of precognition, no mathematically precise theory that said, here I predict a 400 millisecond effect. Why not 4,000? Why not 4 billion milliseconds? Why 400? There's just, so if you can't even answer basic questions like that, scientists, they'll ask you that question, you can't answer it, and they'll go, come back when you got something serious. And that's the way the game's played, and it's right. I mean, I actually agree with the scientists on this one. You know, come to the table with something, or don't bother us.
And this may be an obvious answer, but I feel like it's important to answer it nevertheless. Why do we need to investigate reality in the first place? What are we really trying to do? Why investigate consciousness? Why investigate reality? What's the point of it in the first place?
Well, that's a really good and deep question, because it, from a point of view in which consciousness is fundamental, and you have this idea that there is this awareness that's prior to any particular conscious experience. There's an even a question like yours, but even prior, which is, why should the one awareness be interested in any particular experiences at all? Why bother with spending time in four-dimensional space-time on Earth? Why do that? Why? So if the one consciousness is in some sense just pure awareness without any particular content, why does it bother with any particular contents at all? So that's really your question, but maybe pushed even a step back. And my guess is, and it's just a guess, because these are deep waters, but my guess based on Gödel's incompleteness theorem is that there's no end to mathematical structure to be explored in principle. It's not possible to know all mathematical structures. In principle, it's not possible. It's never ending. It's literally, there's no end to the exploration of mathematical structure. And if consciousness is all there is, then mathematical structure can only be about consciousness and its possibilities. And that means that consciousness has no end to the exploration of its possibilities. In principle, it's a completely open-ended exploration. And ultimately, even the quote unquote one consciousness, in some sense, is completely open-ended. Its potential is never explored fully. And so perhaps that's what consciousness is up to. It's the kid in the candy store exploring all of his possibilities, all the varieties of consciousness. And here on Earth, with a four-dimensional space-time, we're just avatars of that consciousness is put in this particular setting to explore certain of its possibilities. And so science is one way that it gets serious about exploring certain aspects of its potential. Mathematically serious, really, really precise. Of course, then it explores it in other ways as well, like music and art and dance and literature and so forth. It's exploring it. So, math isn't the only way it explores its possibilities, but when it decides to explore itself that way, then that's what it is. If you're going to be a musician, then you want to be good. You want to like really explore. You don't want to be like Hoffman, which is nothing. You want to be explore like a Bach or a Beethoven or Mozart or something like that. Not a Don Hoffman. So I the exploration, that's my best guess right now is the Gödel's incompleteness theorem entails that consciousness has a never-ending self-exploration ahead, and that's what we're up to. And part of the exploration might be just being a cow, standing on a hill, chewing grass, and watching the sunset. That's also part of the exploration of the possibilities of consciousness. So, or being an ant, or being an amoeba. They're just all these different varieties of exploration. So that's a long answer to your question, but that's the best I've come up with so far. And I'm probably wrong.
Why do you say you're probably wrong? That's a very humble thing to say as well. What you're probably wrong, but why do you say that?
Well, partly because if you look at the history of science, for example, in the late 1800s, many physicists were very sure that physics was done. They had Newton, and the laws of Newton were the final story, and they were in some cases discouraging bright young students from going into physics. If you were bright, you needed to go someplace where you could actually make a difference because physics was done. And looking back, we laugh. Physics was not done, and there were many, many brilliant explorations ahead and discoveries. And so anytime that we think that we've got it, we're being rookies, we're being absolute rookies. It's not a matter of humility, it's a matter of not being stupid. We know from the history that we have this habit of believing we're done. And we just have to wake up and realize there are principled reasons for recognizing that we'll never be done. Again, things like Gödel's incompleteness theorem. There is no end to the exploration of mathematical structure. End of story. There is no end. And so what we know is basically trivial compared to what we don't know. And as long as we understand that everything that we know is trivial, effectively, compared to what we don't know, that's a good foundation for our exploration, because then it's not a matter of trying to be humble, it's a matter of trying not to be stupid. Right? We actually know that that we don't know. We know that see, that's the nice thing. We know that we don't know. So we know that it is stupid to be arrogant. It's just stupid. So I don't want to be stupid.
And you mentioned that the one awareness may explore itself through a cow or amoeba or whatever, or Donald Hoffman. Why have you particularly decided to explore consciousness or awareness through the mathematical structure of things?
Well, partly because I have a collaborator who is actually good at mathematics where I'm not. And so so Chetan has been a great friend and collaborator for several decades, more than 3 decades. And so that working with him has allowed me to be able to think freely and creatively and to do what mathematics I can do. But then when I get in over my head, which is very, very quickly, I can talk with Chetan and he helps me go to the next level. And then he tutors me and and I learn new mathematics from him all the time. And so because I have good class, also, Manish Singh and Robert Prentner and Chris Field, these guys are really, really sharp. And so being surrounded by these really brilliant people gives me the freedom to, be a little creative, a little go out there and on the limb, because I know that we can eventually bring the mathematics along and see where we've stepped too far, where we've sawed the limb off and fallen off ourselves, and where we actually have something that's worthwhile. So for me, that's one reason. But the other reason is it's real easy to come up with little theories. Everybody has a theory, and it's very easy to believe your theories. What I want are theories that tell you their own limitations, where the theory itself precisely tells you where it stops, what it can't do. Because otherwise, it's very easy to be dogmatic about your beliefs. And another thing we've learned from history is that basically invariably, when you, not just in science, but in religion, when you know that you're right, then you're almost surely wrong. And so dogmatism, again, is a rookie mistake. It's closing off inquiry when you really should be opening up new modes of inquiry and humbly looking forward and exploring what you don't know. And so a scientific theory that's mathematically precise helps counter our tendency to be dogmatic. It doesn't, scientists are people like anybody else, and so scientists can be dogmatic as anybody on the planet. But scientific theories in the scientific community, as a community, is not dogmatic, because one scientist will try to take down another scientist's theory. So that's how science progresses. And so I love the mathematical rigor, because it forces you to be very, very precise about your ideas, and then it makes them testable, and it tells you their limits. So I'll give a concrete example. So Einstein, like 1907 or something like that, had what he thought was one of his happiest thought of his life, which about gravity, which was if he was in an elevator, standing on a weighing scale to weigh himself, and all of a sudden the elevator went into free fall. Someone cut the cable and it fell and started going free fall. All of a sudden he would weigh nothing on the scale. That was his insight. That was sort of the key idea that led to his theory of gravity. And it was a brilliant idea. But what did Einstein do? Did he just stop there and go, "Oh, great idea, now I've got it"? No, what he did was he then spent like 7 or 8 years wrestling with that idea, learning what at the time was exotic new mathematics, or exotic Riemann's geometry, Riemannian geometry. He had to learn all that stuff, and it was tough, all this tensor analysis and so forth. And then in 1915, he finally, after years and years of struggle and effort, his big idea that he'd had 8 years earlier, he finally wrote down an equation, the Einstein field equations of general relativity, which have transformed science. And a year later, a year or two later, a German soldier, apparently a brilliant mathematician as well, named Schwarzschild, in the trenches apparently of World War I, was playing with Einstein's equations. Smart guy to be able to do that even in a war situation. And he discovered what we call the black hole solutions. And so he wrote to Einstein, and Einstein didn't know that his happiest idea in his life entailed that there would be black holes. He didn't know that. But it was when you take mathematics to your ideas and make them very, very precise, that your ideas, the mathematics comes back and it becomes your teacher. Even though it was your idea and you wrote down the mathematics, his own mathematics became his teacher. He became the pupil of his own math. And then his gravitational theory, his theory of space-time, together with quantum field theory, which is also assumes space-time as fundamental, those together tell us precisely that space-time which was Einstein's idea, the fundamental reality was space-time, that it can't be the fundamental reality, that space-time is doomed. His own mathematics tells him that the very concept that he mathematized, namely space-time, cannot be fundamental, and that it actually falls apart at 10 to the minus 33 centimeters. At the Planck scale, it ceases to have any operational meaning. Now that is brilliant. That is the spirit of the scientific enterprise. It's having wonderful creative ideas, struggling sometimes for years to make them precise, and then having the precise theory come back and slap you in the face and say, did you know this means there's black holes? Did you know this means that your very concept of space-time has no meaning beyond 10 to the minus 33 centimeters and 10 to the minus 43 seconds? So you have to look for something deeper than space-time. Space-time is doomed. You'll have to find something beyond space-time. That's why I go after mathematics, is because you only when you make things precise like that can you become the student of the theory.
Could we define what you mean by space-time exactly?
So for Einstein and for physicists, it's there's a mathematical structure that has 4 dimensions, the dimension of time and 3 dimensions of space, but they have opposite signature in some sense. If you take the unit of time, if it squares, say, to -1, then the units of space square to +1. They have opposite signs in their squared magnitudes, and so it's a mathematical structure that enjoys certain symmetries. The so-called Poincare group is the group of symmetries of space-time. So space-time in special and general relativity is a mathematical structure. In his general relativity, it's allowed to curve. So he uses Riemannian geometry to have a curved 4-dimensional space-time. So it's really a geometric object, a 4-dimensional geometric object that has a certain curvature to it that encodes the effects of gravity. And in string theory, they'll move it up to more dimensions, 10 or 11, for example, dimensions where you have some dimensions perhaps curled up inside the 4 dimensions of Einstein's space-time. But now physicists have found new structures entirely outside of space-time. So his own theory said space-time is doomed. You need to find something beyond space-time. So in the last 10 years, physicists have been doing that. They've said, okay, space-time is doomed. Einstein's theory and quantum field theory tell us that. So what's outside of space-time? And they found the amplituhedron, and also the deepest thing they found are decorated permutations. So they found these new structures entirely outside of space-time, but you can show how space-time arises as a projection of these structures. So yeah, that's sort of what space-time is, and also a little bit about the mathematics of the structures outside of the space-time, but we can go into that more if you want.
So if space-time is not fundamental, we're suggesting that awareness is fundamental or consciousness is fundamental. What's your proposal?
Well, of course, from the physicist's point of view, that's not what it's about, right? Space-time isn't fundamental. They're not going to be saying that therefore entails consciousness or awareness. Most of them wouldn't go there, and they would probably laugh. What they're doing is saying we're going to find new mathematically precise structures beyond space-time that can predict our data, like scattering data at the Large Hadron Collider or other colliders. So for me, I'm a cognitive scientist who has been interested in consciousness and its relationship to the brain and neural activity and so forth. And the utter failure of attempts by me and my colleagues to come up with a theory in which the brain or neural activity or even some physical systems more generally can create consciousness. The failure of those to explain any specific conscious experience. What is, for example, Hameroff and Penrose's idea about orchestrated collapse of quantum states of microtubules in neurons, or integrated information theory approaches, which could be interpreted as not necessarily physicalist, but in fact usually are thought of in physicalist terms. Those theories and others like them, none of these theories can explain, for example, the taste of chocolate. What is the pattern of integrated information that must be the taste of chocolate and could not be the smell of an orange? There's not one success, not literally not one specific conscious experience success anywhere. And so that utter failure, complete and total failure to explain even one specific conscious experience, and then recognizing what the physics is telling us, that space-time isn't fundamental, and that therefore objects in space-time, like neurons and microtubules and quantum states of electrons and microtubules, none of these things are fundamental reality. And then the Nobel Prize that was handed out just last month to 3 physicists for the experimental confirmation that local realism is false, that physical objects, the idea that physical objects have definite values of real of their properties, like position, momentum, and spin, that have definite values and with effects that travel no faster than the speed of light. That assumption of local realism is false. It's just plain false. So when space-time is doomed and local realism is false, then the very foundation of which my colleagues and I have been studying consciousness, namely that physical objects somehow create consciousness, that's already been dismissed by physics. That's not the foundation. So if I'm going to get a theory of consciousness at all, it can't be from within space-time, because space-time is just not deep enough. It's in fact, space-time, from my point of view, is a very shallow data structure. It's 10 to the minus 33 centimeters. Not 10 to the minus 33 trillion centimeters, just 10 to the minus 33 centimeters. It falls apart. So we have a cheap, very, very cheap data structure here, very, very shallow. And we've been using it because that was all we knew. But now in the last 10 years, we've found new structures outside of it. And so what I've been doing is saying, well, look, it's silly to take space-time as fundamental when physics tells us it's not. But what if we could start with a theory of consciousness and boot up space-time from the theory of consciousness? That would be a very useful next step in science. So can we do that? And so that's what I've been working on.
And let's say we discovered that what yourself and your colleagues are doing is true, that we've verified this mathematically and we have the structure. How does that affect our daily human lives?
If this idea is, I won't say that it's true, but I would say, what if it's a useful next baby step? It turns out to be a very, very useful next baby step in science. Then I would say the impact will be completely transformative on society, because once you have a grasp of at least a layer or two beyond space-time of what's going on, the technologies that you're going to open up are transformative. Just to give an example from history, when Faraday was playing with magnets and wires and iron filings and frog legs, he did all these wonderful, brilliant experiments. Well, what an interesting hobby for some, why doesn't he do some real serious work? I mean, what's he doing playing with frog legs and wires and magnets and so forth? But he does all these wonderful experiments, and then this guy, James Clerk Maxwell, comes along and looks at it and says, hey, I can write down a few equations which summarize everything, all of your experiments. So the decades of Faraday's work and the brilliant experiments boils down to one set of equations that captures the whole thing. And that then launches the revolution that's here we are. I'm talking to you. I don't know even where in the world you are. We're talking by Zoom from different spots in the world because of the technology that was unleashed by that mathematics and then the insights that came from it and then the technology. So here we are. Space-time is not fundamental. It's just a data structure. It's like a virtual reality headset that we have. And we've been really good in science at exploring that headset. We've become real experts at understanding the headset. So it's I like the example of virtual reality, like a game of Grand Theft Auto in virtual reality. We've become the wizards of the Grand Theft Auto world. We know how to design the cars in that world and so forth, or drive the cars in that world. But if you're the wizard and you can beat anybody on the game, you're nothing compared to the software engineer who wrote the program and can take the gas out of your car, give your car a flat tire, or even change the geometry of the roads. If you know the software that's running the game, you can change the rules of the game itself. So if space and time are not fundamental reality, and they're just a headset, they're just a VR game that we're in, and we get a first baby step into the software behind the game, then we can start to play with the game itself in ways that are completely transformative. One example I like to use is, more than 90%, I think, of the galaxies that we can see, we could never get to because they're moving away from us at faster than the speed of light. So if we move through space-time, the fastest we can move is the speed of light, and we'll never get to them. So there's all this real estate out there waving at us saying, here we are, and you can never come visit us. Well, that's because we're limited right now with technology going through space-time. But space-time is just a data structure. It's not the fundamental reality. And once we know some of the software outside of it, we don't have to go through space-time. We can go around space-time. We want to go to Mars. We don't have to hop on a ship and go through space-time to Mars. We can just go around space-time. So when you start thinking that way, the technologies that we could open up are truly mind-bending, which is completely mind-bending.
Could you define what you mean by going around space-time?
Well, so in the VR example, if you put on a headset and bodysuit and you're driving a virtual reality car in the VR Grand Theft Auto game, you're having to play by the rules of that game. I can turn my steering wheel, I can push on the gas. Those are the things I'm allowed to do. Like I can get out of my car, maybe I have a gun if it's that kind of game. There's some certain things that I can do. But if I want to get from A to B in the game, I have to go through a certain space in the VR game. But if I'm a software engineer playing the game, I can just, for example, take my car and say, well, my car right now is in California, but I'm just going to change this parameter in the code. You know what? Now my car is in New York City. I just changed the parameter. I changed its XYZ location in the code. I didn't have to actually go through the space, pushing on the gas and steering the car. I just put it there because I have the code that governs that data structure. So I can just put it there. So that's the kind of metaphor that I'm talking about. Once you actually understand that code, if you can start to change the code outside of space-time, then you will have dramatic effects inside the space-time.
But in terms of, I know that's a metaphor, but if we were to look at it as our actual, what we perceive, how would that change? Like, how would we go around space-time in what we see, if you know what you mean, in the actual art?
Well, I can only guess, but the guess I might have is like this. Suppose that I again with the VR metaphor. So suppose that there's some guy who's a wizard, and he's driving his Ferrari, and I'm the software engineer, and I decide that I need to play with the guy a little bit, and so he's driving on a street. And I just go into the code and I change a little bit of code. And now his car is in the middle of the air over the Grand Canyon. And that's where he is right now. So he was just driving on the street, and all of a sudden he just sees himself his car is in the middle of the air, a mile above the bottom of the Grand Canyon. Now he's scared to death, right? He's like, "Whoa, how did that happen?" So for him, he would just see something just changed, something just happened, because that's all that he can see is what he sees through the headset. But outside, what's happening is some parameters are being changed in the software itself. So that could be one way that you would experience it, is just, whoa, all of a sudden there was a sudden change in my surrounds.
And when you say software in this example, software in this case would mean what? Awareness?
So software in this case would mean, again, this is assuming that what we're doing might be a useful next baby step in what's going on. So we have there's a little bit of background to just say. So the software that I'm talking about is plugging into some discoveries that the physicists have made. So I mentioned earlier that the physicists say space-time is doomed, but they haven't just thrown up their hands and go, "Oh well, what do we do?" They found these new structures. They found the amplituhedron, they found cosmological polytope, sociohedron, and the deepest thing they found are something called decorated permutations. And permutations are like shuffles. So if I have a deck of cards, there's all sorts of ways you could shuffle the order of those cards. And each different shuffle is a different permutation of the cards. So surprisingly, the notion of permutation is the deepest structural notion they found so far. It's a little twist. It's called a decorated permutation, and we can go into that twist if you're interested. If your audience is more technical, we can go into that. But they found these things called decorated permutations, and so what I and my team have done in the last few months is we have this dynamics of consciousness outside of space-time, and it's built on called Markov chains, so the mathematics of Markov chains, the Markovian dynamics. And so a few months ago, we basically said, look, we have this Markovian dynamics of consciousness outside of space-time. The physicists have found decorated permutations beyond space-time. That's the deepest thing they found, but nothing dynamical. These are just static structures they found, the amplituhedron and decorated these are just these geometric or combinatorial structures beyond space-time, but no dynamics. And physics likes dynamics. But we have a dynamics. So perhaps Markovian dynamics could project onto these decorated permutations, and we could then take the next step beyond what the physicists have found. So we said, let's just look and see. Surely the mathematicians have explored whether you can take Markovian dynamics and project it onto decorated permutations. That seemed like a pretty straightforward mathematical question. So we did a literature search, and it hadn't been done. So we did it. We discovered a mathematical map that takes our any Markov chain and gives a canonical projection into decorated permutations. And so that means now that we have a map for which is dynamics of consciousness, which is really complicated, can project down to decorated permutations. And then the physicists say, if you give us decorated permutations, we can take you all the way into space-time, and we can predict scattering amplitudes, like when particles hit each other, like maybe an electron hits a proton and things start scattering out of it, right? Those kinds of scattering events, they can predict that just with the decorated permutations outside of space-time. So that's what we did. We have this theory of consciousness, conscious agents, in a paper that we just published last week. So it's called Fusions of Consciousness is the title of the paper. And in that paper, we write down this mathematics of conscious agents, and we give the precise mapping from that onto the decorated permutations, which then means that we have now a map in principle from conscious dynamics all the way through decorated permutations into space-time that should be able to predict all the scattering amplitudes in all the collider experiments. So that's what we're working on now. But that's the idea, is to now have a mathematically precise theory that that then allows us to make predictions that we can measure and test inside space-time.
Right. Well, look, Donald, I'll be honest, I'm not completely technical. I don't necessarily know what you mean when you use all these terms, but I hope somebody out there can understand these things. But yeah, I'm not necessarily a very technical person, so I don't even know what to ask in regards to what you just said there. But I did want to ask, when you said that space-time is doomed,
Yes.
and then we proposed that perhaps consciousness is fundamental, and then you said a lot of scientists wouldn't accept that. They would
Right.
laugh at it. Why is that the case? Why do we laugh at such a notion if we don't know?
Well, partly because there's been a history in which people talked about consciousness but weren't precise,
Mm-hmm.
and 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 so they've made no that whole dialogue has made no contribution to the advancement of our knowledge. So and there's another reason though, and that is that the success of Einstein's theory and quantum mechanics and so forth um, has led many physicists to think that it was all wrapped up. A lot of people have thought, again, we're all done. Space time is fundamental, and we've got it pretty well wrapped up. It's really been the theories themselves that tell us that space-time is doomed that has gotten a few physicists to really start looking beyond space-time, but most physicists are not, right? It's really mostly the high energy particle physicists who are looking for new structures beyond space-time. The rest of the physicists, I was at a conference a few months ago on consciousness where there were some quantum physicists who are working on consciousness. And for quite a few of them, after their talk, I would ask them, so what do you think about the new structures that physics is finding beyond space-time, like the amplituhedron and decorated permutations? And to a person, none of them had even heard of these structures. And they are professional physicists, they're PhDs in quantum theory.
Mm.
So this is not really widely known even among physicists. It's really so if it's not, it seems technical to you. Well, it's not known to many physicists right now either. The only reason I'm aware of it was because I was looking for anything in physics where they might be going beyond space-time. I was looking for that, and so there is this group, and it's the high energy particle physicists like Nima Arkani-Hamed, Yaroslav Trinka, Juan Maldacena, and guy named Benincasa. Sorry. Who are doing these kinds of studies, and quite a few. I'm just mentioning a few of the names. So there's a big group now, but it's a specialty. It's a high energy physics group, and so most physicists are quite happy to be solving problems inside space-time, quantum theory kinds of problems. But the high energy physicists, again, like Nima and collaborators, what they say is not only is space-time doomed, but quantum theory is doomed. Quantum theory is not fundamental either. And what they're showing is that quantum theory and space-time emerge together, joined at the hip, so to speak, from deeper structures like decorated permutations and the amplituhedron. And so it's the structure of these objects beyond space-time. They're like, think of them as like diamonds or something like that, these multifaceted high dimensional structures. So they have faces and edges and points and so forth. And it turns out that the whole structure of the faces and edges and points codes for the properties of space-time and quantum theory, technically locality and unitarity. But so space-time and quantum theory are not fundamental, and there are these deeper structures that don't have any so-called Hilbert spaces, so they're beyond quantum theory, and they could have trillions of dimensions. The amplituhedron could have trillions of dimensions, whereas space-time has 4 dimensions, or maybe 10 or 11 if you're doing string theory. But these are structures entirely outside of space-time. So again, most physicists aren't going there. and it's no surprise. It's only a few physicists whose work has forced them to go there, and it's going to take a while for the rest of the physics community to understand and come along. And again, that's no surprise. But if you go back in history, in 1905, Einstein published his special theory of relativity. Well, that was the end of the road for Newton's notion of space-time to be fundamental. That was it. It was over. But 17 years later, in 1922, when Einstein was getting the Nobel Prize, the Nobel Committee, and so these are people who know some science, the Nobel Committee were very clear that they were not giving the prize for anything to do with Einstein's theory of spacetime, special relativity or general relativity. They were very, very clear about that. They didn't buy it yet. Well, that's so, and they were not dumb. They just, so it takes a while, and so that's what's going to happen here. It's going to, the amplituhedron and the decorated permutations. These are structures that are basically, they're beyond space-time. They allow you to compute scattering amplitudes much more easily than if you do it in space-time. If you do it in space-time, something that might take you hundreds of pages of algebra to compute for one interaction, you can do it with 2 or 3 terms by hand when you go beyond space-time. So the math all of a sudden becomes much, much simpler when you go beyond space-time. And you see new symmetries that are true of the data, but you can't see them in space-time. So it's completely over for space-time, and it's also over for quantum theory. They're not fundamental. But it's going to take decades for the rest of the physics community to come along and to jump beyond space-time into this new realm. But I don't want to wait. We're trying to get this theory of consciousness booted up. The physicists just in the last few years, in less than the last 10 years, have discovered this decorated permutations beyond space-time. And we're saying, thank you. Oh, that's the interface we needed. So we can plug our theory of consciousness right into the interface that you gave us. And so the next paper I'm working on is now to explore that. Now that we have this map from Markovian dynamics of conscious agents through decorated permutations into space-time, that math told me where to look in my theory. It says something called communicating classes. So this is a particular property of these Markovian dynamics. It's something called communicating classes. Those are the items of interest. That's the part. So it's properties of communicating classes that will get mapped to physical properties like mass and momentum and energy and so forth in space-time. So that was why this mapping was so important, because it now tells me where to look for so the next paper we're working on is to now make those correspondences really precise, and then we can start to make really explicit experimental predictions that can be tested in colliders from the theory of consciousness. So that's where I'm headed next, is to really, we have the bridge, now it's time to bring the heavy equipment across and make really, across that bridge, and make really detailed predictions that we can go test at colliders. So that's my goal. Start with the theory of consciousness and make absolutely precise predictions, or even better, take the data that the physicists have already gotten and show that we can model it completely to every detail from this theory. So that's what I'm up to now.
And what kind of predictions are you hoping to make? When you say experiment, do predictions, what do you mean by that? What kind of predictions?
So the one that I'll be planning to work on this year is the inner structure of the proton. So everybody knows that the atom has a nucleus made of protons and neutrons, and the number of protons determines what the chemical element is. If it's got 1, then it's hydrogen. If it has 2, it's helium. If it has 3 protons, it's lithium, and so forth. If it has 8, it's oxygen, things like that. And then there's electrons that are going around the nucleus. But for the last few decades, physicists have been studying the proton itself. What's inside the proton? And they for a while thought it was just 3 quarks. these things called quarks, and they're tied together by gluons. But as they've gotten more and more powerful colliders that can use higher and higher energies and look at smaller scales, both distance and time, what they found is at the smallest scales, when they look at a proton really, really closely, and small temporal windows and small spatial scales, it's a sea of what they call gluons. These are massless particles. They're bosons. They're massless and it's just like this high energy sea of these massless particles. And then when they back off, when you start to look at bigger and bigger temporal scales, then you start seeing quark-antiquark pairs appearing. So now these are massive particles. The quarks have mass. And then, but now it's a quark sea. So it's and sea in like an ocean. It's an ocean. There's just a bunch of these things. So there's an ocean of gluons appearing, just disappearing and then dividing and then disappearing. And it's just like chaos. And then and it's a massless chaos, so high energy, pure energy. And then at a longer time scales, you see an ocean of chaos, but now you're seeing what they call fermions, massive particles, quarks and antiquarks appearing and disappearing, and then when you get to the very largest scales, then you still have a lot of this dynamics going on, but then you get three dominant quarks that are appearing. So what I want to do is to use the theory of conscious agents and this mapping into spacetime to predict exactly this pattern. At the highest spatial and temporal scales, you get this sea of gluons, and then you get a sea of quarks, and then you get, at the largest scale, you start to see three quarks. And it's a little technical, but with these Markovian kernels, you have a big conscious agent with lots of states that it's, dynamics of. Any subset of states in our theory is also a conscious agent. So maybe I started with 1 billion states, but if I take a subset of 50 of them, that's the subset of 50, that also defines a conscious agent, which is a subset of the bigger agent. And so any subset is also an agent. And I can look at the projection of the big dynamics onto the states of the little agents. In Markov language, it's called the trace. It's a trace chain. So I have a big Markov chain, the big dynamics, but I can induce a Markov chain on the subset for this one little agent called a trace chain. And that will be what the little agent can see about the big one. It's not going to see everything. It's losing information, but it will see a trace chain. And what it sees will depend on the number of states. So you can call that its spatial window. How many states does it have? But also the temporal window. How many steps of the big process? How many? Maybe 50 steps of it, or 100 steps, or 1,000,000 steps. How many steps of it are you using to create the Markov chain on your little subagent? And in simulations I've already done in Mathematica, I get exactly the qualitative pattern of results that I just described. I get, using this new connection that we've made from the dynamics of conscious agent through the communicating classes into spacetime. And one other key, I think, idea that I hope it holds up, something that is called the entropy rate of the communicating classes corresponds to mass. So that, giving that one other claim, that the entropy rate of these communicating classes corresponds to what will project to mass, then I can predict qualitatively already the results of the gluon sea, and then the quark sea, and then the three gluons. And I can even go beyond and say that at the very largest time scales, the whole thing will end in an entropy death. So I actually, it actually is not just a model of the proton, but actually a model of high energy, essentially Big Bang, all the way to an entropy death of the whole thing. And it's all an artifact of the statistical accidents of the sampling that you get in this trace chain process. So none of it, all the particles that you're seeing are not an insight into reality. They're artifacts of statistical fluctuations in the sampling process. So if we can show that, that would be that's what my goal is for this year and for the papers this year, is to show that the gluon C, the quark C, and so forth, is really not an insight into these pre-existing particles. Rather, what the particles we're seeing are sampling artifacts of a trace process, of conscious agents. So if we can do that, that would, I mean, it doesn't mean that we're right, but it would certainly mean that this idea of consciousness being fundamental needs to be taken seriously. But you can see the level of the game. This is not hand waving and saying, well, I think consciousness is fundamental and you should take. It's saying, no, no, we're going to try to predict the exact momentum distributions that have been obtained over decades of experiments at these colliders. And we're going to try to actually show that we can get exactly those momentum distributions of the quark C, the gluon C, and so forth. And then we'll give you some new insights. We'll point out that these particles are not pre-existing entities. They're artifacts of statistical sampling issues. And that then should lead to some new technical predictions. And that's what I'm looking for in the next couple of years, is hopefully to not just model the current data, but then make new technical predictions. If we can make a new technical prediction that is then verified, then consciousness has a place at the table. That's my ultimate goal. Is then we have a place at the table. But I should say this, that our result that Markov chains project to these decorated permutations, and therefore we have a kind of dynamics beyond space-time that physics could be interested in. We don't have to interpret that dynamics in terms of consciousness. If a physicist doesn't like consciousness, that's fine. At least we've contributed the idea that there is a dynamical system, namely Markov chains, that does project to what you found, namely decorated permutations. So if you're looking for dynamics, there is at least this class of dynamical systems that will work for you. You'll have to, if you don't like consciousness, then you have to say a dynamics of what? What else? What is this a dynamics of? And whatever it's a dynamics of, it's a dynamics of something beyond space-time. So it's not going to be a physicalist. Whatever you do here is not physicalist anymore in terms of at least space-time physics. It's a trans or beyond space-time kind of entity that we're dealing with. So it's not going to be comfortable for anybody. If you don't like consciousness, whatever you stick there is not going to be comfortable. It's something beyond space-time. So we'll have to pick our poison. I've picked consciousness, but they could pick something else.
So essentially, I'm just going to try to summarize what you just said. Basically, are you just trying to, well, we're saying that consciousness is fundamental, and you're just doing these experiments to show that may be so. Is this what we're doing? Is that the reason why we're doing these predictions in the first place?
Or to show that I'm wrong, right? But yes, I mean, so well, the nice thing about this is, suppose that it turns out that, I have this model of consciousness, and yeah, we got this map of the Markov chains into decorated permutations, but it turns out that there's no way that I can find a dynamics that leads to the momentum distributions that the physicists have found. Well, then I'm wrong, right? There it is. I'm wrong, and I had fun, and I was wrong, and that's not the right dynamics, and so either way. So, but the idea is to be absolutely precise so that we can actually make progress. It's one thing to say I know the truth, but it's another thing to write it down and then go test it.
Essentially, to me, it seems like that's all we're doing, right? Just exploring the truth. So why else? What's the point of physics? If they're dismissing all of this, well, not all of this, if not that they're dismissing it, but you said it's taken decades to reach this. What's actually the point of physics? Why do we do it in the first place?
Well, I think each person who does it has probably their own motivations, but I can say a couple of the motivations that I think that might be common. One is just pure curiosity. So many physicists is just like, why does it work that way? You have a magnet, you see the iron filings going in circles and so forth. You go, okay, this seems like magic. What's going on here? Why do the iron filings do that?
Mm.
Or how in the world is it that I'm talking to you using something invisible? Okay, give me a break. What is that? This seems like magic. So what gives here? Maxwell's equations. Why are those equations true? Where did they come from? Are they written in stone somewhere? Why should those equations be the way things? So there's just this pure curiosity. Sometimes it's driven by other motivations. World War II, it got driven by military, right? And we really pushed on studying fission and really understanding fission better, and technically as well, experimentally as well as theoretically, and then fusion, and that led to bombs. So there's practical reasons for it. I think many scientists are driven by the curiosity. It's just like, who ordered that? Everything is, when you start to really look at the stuff, there's surprises everywhere. Why should the universe be that way? Who wrote? Why those equations? What's going on here? And so you just want to explore it, and so those are some of the kinds of motivations. For me, it's I guess it's the curiosity. I mean, I talk about these technical things, but that's not really what drives me. The kinds of technological inventions that may come, partly because I doubt that those will come in time for me. I mean, I think I'll be dead before the stuff is advanced far enough to really, for example, go to the Andromeda galaxy outside of space-time. I'd hope to be alive. I can hope for it, but realistically, I sort of doubt it. So it's not really the technology that's driving me. It's right now it's just the pure curiosity. But what we found is when we make these scientific advances, they do lead to technology that's game changing, right? Like the technology we're using right now to talk to each other. This would not have been possible without the advances in physics. And so it's a double-edged sword, because the technology that comes out of our basic science can be used to improve the lot of humanity. It's allowing me to talk to you, and I probably wouldn't have talked to you otherwise. So it connects us in ways that we wouldn't have been connected otherwise. On the other hand, we see the advanced devastation that we have in wars from the new technology as well. So it's double-edged. It's more power for good and more power for destruction. And so that's sort of a long answer to why we do this. I think there's a variety of motivations.
And how did this model answer questions such as, what is wisdom? What is joy? What is intelligence? What is happiness? Because it seems to me like religions have spoken about this to a certain extent. Well, spirituality. There's all these fields, and perhaps we're all just talking about the same truth, just through different words, through different lens, through different theories. But essentially, aren't we just fundamentally concerned with the same question?
That's a great question. An interesting background. Most of my colleagues in the sciences who are physicalists would say that intelligence and joy and emotions and love and these things are merely byproducts of the activity of neurons in chemicals in the brain. And so from a physicalist reductionist point of view, they would say that these are not fundamental, and ultimately any emotion is nothing but a complex pattern of activity in some neural system somewhere. And and then they would argue that the evidence for that is, for example, if we play with the neurochemistry of your brain, we can change your emotions. We can alter your emotions. And I beg to differ, because I think that space and time are doomed, and so they're not fundamental, and neurons don't even exist when they're not perceived. So I mean, that's a strong statement, but that's when to say that local realism is false, and the quantum theory is not just confined to small physical objects. It's all objects are subject to the laws of quantum theory, all objects in space-time. Local realism is flat out false, period, for all objects. And it's false for neurons. And for me, I'm saying neurons do not exist when they're not perceived. So neurons are not the source of our emotions, of love, of joy, of happiness, of intelligence. They are our user interface description to a world beyond space-time, in which perhaps love and joy and emotions and intelligence is fundamental. And that's the direction where I'm headed with this theory of consciousness, that instead of a picture of a physicalist world in which consciousness is a latecomer and really has no deeper significance, and will eventually be extinguished in the entropy death of the universe, I'm saying that consciousness is fundamental, and so love and joy and so forth are not reducible to objects in space-time. They themselves are, at least in the work I'm working on right now, they themselves are fundamental in this theory. And so ultimately, you mentioned intelligence. I think that, so this is now, I won't now speak as a scientist. I'll just speak about my own thoughts on this, because I can't back this up with a hard model. But I think that although I can hint at it, I guess, with some science, I think that this fundamental awareness that comes up in this model of consciousness is an infinite intelligence. It's an unbounded intelligence. And I think that so this is just like my personal view. I think that there is an unbounded one infinite intelligence, and that what you and I are, and what an ant is, what a cow is, is an avatar that one unbounded intelligence has chosen to take on to explore its possibilities. And any scientific theory that I come up with is ultimately trivial compared to that infinite intelligence. And that's another reason why I don't take myself too seriously. Right, is on the other hand, I take us all equally seriously as avatars of this one infinite intelligence. But I take my own particular new scientific proposal as I said, the next baby step. So I'm not patting myself on the back and saying, hey, you did it, you got the theory of everything. There is no theory of everything. No theory could ever capture the unbounded intelligence that we are. But we are the intelligence that's exploring itself in little bits and pieces through these scientific theories. And that's apparently a worthwhile thing for us to do, even though in some sense we can only touch the surface of the deep reality that we are. So my own personal view is that love and peace and joy and intelligence are profound, deep aspects of the ultimate reality. They're not mere accidents of physics. They are the fundamental reality, and getting in touch with those is getting in touch with our deepest reality of who we are. And that space and time is merely a headset, and our bodies are merely avatars within that headset, in which this unbounded intelligence is exploring a small subset of its potential, a very, very small subset, a measure zero subset of its potential. So instead of space-time being the fundamental thing, no, this is just a relatively cheap headset that we're trying out right now to explore, you know, a small aspect of our potential. And death then is, you know, taking off this headset and maybe trying on a little bit better model. You know, doesn't fall apart at 10 to the minus 33 centimeters. Maybe it goes to 10 to the minus 33 trillion, or, you know, and maybe it's not 4-dimensional. Maybe it's 50,000 dimensional. You know, who knows? So I think that the things you're pointing to, love and intelligence and so forth, I think that we cannot write them off as accidents of impersonal and mechanical or quantum mechanical physical fundamental reality. That's not what they are. They are the fundamental reality, and space-time and quantum mechanics are merely a headset that we use to explore some of our potential.
You know, that's quite interesting. And the question that comes up is, why haven't we paid attention to this as a society? You know, science. Why, like, if we were to discuss this with your colleagues, with scientists in general, would they look at this seriously?
Well, of course, there is a large segment of society that has studied this or taken this seriously for thousands of years, right? The spiritual traditions, Buddhism, Hinduism, mystical Christianity, mystical Islam, mystical Judaism, and so forth. There's a long and profound history of exploration of us as intelligent, conscious beings. But it's that what's happened though in human history is that pursuit has used tools like meditation and charitable works of kindness and so forth, and learning to live together in communities and so forth. And that's been an exploration of human nature and human potential using those tools. It's only been in the last few centuries that we've started with science to use precise mathematics and precise experiments to explore nature as well. And as is well known, there was a big divide between science and spirituality early on, sort of symbolized by the Catholic Church and Galileo, and their disagreements, and Galileo having threatened with torture and to reject his scientific views and that contradicted the church. And so there's early on there was this divide. I mean, many early scientists were believers. Newton was a believer in Christianity and so forth. So there were many who were believers, but there was this divide where even the scientists like Newton, who applied mathematics successfully to the physical world, I don't know, I mean, perhaps I'm missing something, but I don't know of any serious mathematical attempt to apply mathematics to a spiritual realm. Maybe Newton did it and I'm not aware. Leibniz talked about his monads, and these were like perceiving entities, not necessarily, I think, inside space-time. I think they were outside of space-time. And in Leibniz, so Leibniz also was this brilliant scientist and mathematician, a complete genius, and he had this idea of perceptions beyond space-time and the monads, but he didn't himself write down the mathematics of it either. So there's been this history in which scientists applied mathematics to things inside spacetime, to just spacetime and objects inside spacetime, but not to any serious extent to consciousness. And so this is what we're trying to do with this theory of conscious agents, is to rectify that, to say, look, the tools of mathematics and science can be applied to consciousness. We'll never get a theory of everything. That includes our attempts to get a theory of consciousness. We'll never be a theory, but that doesn't mean that we shouldn't have a theory of something. If we can't get a theory of everything, that doesn't mean we shouldn't try to get a theory of something. And so I think we've only had the tools of science for, what, 4 centuries, 5 centuries, maybe, depends on how you count it. Not been that long. If you look at our best estimates, Homo sapiens has been around for hundreds of thousands of years, maybe millions, but at least hundreds of thousands of years Homo sapiens has been around. So it's only been in the last 400 or 500 years that we've had these tools. So we cut ourselves a little slack. So we applied them first to our headset. Partly that was easier, right? We can, rolling balls down inclined planes. That's much easier than taking on consciousness full throttle. So that's what we did. Galileo rolled balls down inclined planes and measured their speeds and the times and so forth, and started. We got equations, and we did what we could. We used our new tools to study our headset, but now we're getting outside of the headset. The physicists, just in the last 10 years, have exploded outside of the headset and found the amplitude-hedron and decorated permutations using those same tools. So now the spiritual folks have been said for thousands of years, space-time isn't it. There is this spiritual realm outside of space and time. Now we have the tools to make good on that statement. We can actually get a mathematically precise model, again, not a theory of everything, but a theory of something, about consciousness, and project it. Maybe we're onto something, projecting that through decorated permutations into space-time. We'll see. But at least the game is on now, where we can get a mathematical model of consciousness and tied in with the last 400 or 500 years of good work on the structure of our headset. Now we can put them together into one package. So that's where I see it heading. And so that's why I think it hasn't been taken seriously before. That was your question, what's taken us so long. I think we really, these are new tools. We just had to learn them. We had to cut our teeth on a simpler problem. Space-time is not easy, but it's a much easier problem than consciousness full on, because consciousness is far more complicated, and space-time is just a little headset. The whole point of space-time is to simplify things. So from my point of view, space-time is nothing but a simplifying device that conscious agents use for their interactions. So we focused on the simpler part of the thing, which is a good place to start. Learn your tools on the simple thing before you try to take on the bigger problem of the complexity of consciousness more generally. Long answer to your question.
And if we're never going to get a theory of consciousness or a theory of everything, what else is there to do as avatars on this Earth? Well, so-called Earth.
Well, I think science is just one of thousands of activities that we do. I mean, I think that dance, art, music are just as much an exploration of the possibilities of consciousness as any scientific theory. They're just in a different venue, and I wouldn't say one is more important than another. I would say that they're all unequally ways in which consciousness explores and enjoys and celebrates its many potentials. Even eating a piece of chocolate, there's a lot of joy in that as well. So I would say that I would not want to claim that what we're doing is more important than anything else that's being done. It's just one of the venues that consciousness is using to explore itself. But art, literature, dance, music, politics, these are all different ways that consciousness is exploring. Being an amoeba, being a bacterium, being a starfish, being a jellyfish. These are all ways that consciousness is exploring itself, and if there is just one consciousness, then there's a deep sense in which I've been a jellyfish, I've been a starfish, I've been an amoeba. I'm exploring all those things, and even that isn't even beginning to scratch the surface of our potential, of the one's potential.
And if we're speaking purely of human potential as avatars of consciousness, do you think we're going to ever reach this potential if we all have different theories as opposed to how things actually are, but as opposed to just looking for the actual truth of things? If that makes sense as a question, because it seems to me like there's still war happening, there's still pollution, there's still hatred towards one another. And why? For what reason?
Right. Well, of course, on the one hand, I would agree with someone who says that we need to do whatever we can to help the human condition, to reduce disease, to prevent wars, to stop wars, to make life good for us and for all other animals and plants and so forth, for the environment. So absolutely. So there's a question, why, if there's this one good consciousness, why is it letting all this happen? And why all this pain and so forth? And how does that come out of consciousness exploring all of its possibilities? And ultimately, I don't know the answer to that. I mean, so I like to, it's good to pose really tough questions and face our ignorance in the face of those questions. But I think that,
sorry, I don't have a phone number for German
every once in a while,
who would you like to call?
I'll just have to tell Siri to be quiet. So something that C.S. Lewis wrote in one of his books, I forgot. So C.S. Lewis is a very famous British author and Christian apologist, and a genius. But something he wrote, he was, I guess, a soldier in World War I. And somewhere I think I remember reading that he said that he felt that, suppose that he and some young German soldier had both stood up from the trenches, fired at each other at the same time, and both killed each other, and just shot each other and killed each other at the same time. He said he felt that he would have left his body, and the German, he'd go over there, shake hands, they'd laugh about it, and go off. That really hit me. That in some sense, he had this idea that this is just a headset, and the death was just taking off the headset. And so it was almost like, so we're in this VR game, you're with your buddies at the VR game, and you're playing Grand Theft Auto, and you crashed your cars, and your avatars died, and your cars were smashed, and you take your headsets off, laugh, and go have a Coke or something like that afterwards. It feels very serious while you're in the middle of it, but then you take the headset off, and you learn something from the process, and you walk away. And I'm not saying that that's the right attitude, but it's an interesting direction to explore. And there are pitfalls in that direction, because I don't, again, as I said to start with, and I was very careful to say it first, I think that we should do whatever we can to ameliorate the human condition and the environment and so forth. On the other hand, there is this interesting point of view that ultimately it's just a headset, and really no animals were hurt in the production of this film, kind of thing, right? Ultimately, you take the headset off, and you wake up and go, oh wow, and then you go shake hands with the people that you were fighting with. So So I would think that it's worth exploring that possibility, but you can see it's nuanced, because I don't want to go to the place where it says, well, do whatever you like, hurt people. I don't want to go there. We're really here to learn and to grow up and to wake up. And since since it's a real process of learning and exploring, real pain happens, but ultimately, you're okay. You learn something from the process, and you're okay. But again, that's just, so I'm not speaking now as a scientist, and the chance that I'm right is very, very small. But it's an idea.
It's an idea. It's an idea, and it's a tricky subject to talk about as well, because it can be misinterpreted. But I know what you're saying.
Yeah.
I understand what you're saying. It's like, at the end of the day, it's like a game. You just lose the game, but no, not a game.
Right.
Yeah.
You
take off the avatar
no excuse
headset
to hurt people. Yeah, it's not an excuse for hurting people. On the other hand, if that's what's required as part of the learning process, then that may be essential to have that happen. But so it's not the same thing as condoning violence, which I don't. On the other hand, it's understanding it as part of the process.
Well, look, I feel like that's a good opportunity to finish up the podcast. Thank you so much for taking the time.
Very good. Thank you so much, Dom. It was a real pleasure, and thanks for inviting me.
Thank you.